In this section, we'll be looking at real-life applications of functions that can be used to model real-life things as either a linear model, a quadratic model, or an exponential model. So some of these are going to give us a table of values, which we can just then use to basically, that we know that like if the first difference is consistent, then it's a linear function. If the second difference is constant, then it's probably a quadratic, or if the first differences are a multiple, it's probably exponential. So let's just look at the first one. It says a window cleaner is cleaning windows about halfway up the Peachtree Plaza Hotel in downtown Atlanta. The cleaner didn't properly clip on one of the squeegee tools and it fell from 400 feet up in the air. The height of the squeegee t seconds after it fell is given below. What type of function, linear, quadratic, exponential, would best describe the squeegee's height as a function of time? So really all we need to do here is compare and look at like the differences to see if it fits any one of our models that we're familiar with. And the x's are changing by 1 consistently, so that makes it easier to look at the first differences below. So from 400 to 384, that just went down by 16. And then from 384 to 336, again, if you're needing some help with this, what we can do is we can just subtract the second one minus the earlier one. So like 384 minus 400. Or that's where I got the negative 16 from, 336 minus 384. You can see I'm going to get negative 48 for that. And then from 336 to 256, so 256 minus 336 would be negative 80. And then 256 to 144, so 144 minus 256, you just take the second one, subtract it, so negative 112. And the last one looks like it would be negative 144. All right, clearly it's not linear because it's not, the first differences aren't constant. And it's kind of hard. It could be a multiple because negative 16 times 3 is negative 48, but negative 48 times 3 is not negative 80, so it's not that. So hopefully it's quadratic. Let's look at the second difference. All right, from negative 16 to negative 48, if we look at negative 48 minus negative 16, so I typed in this negative 32. And then from negative 48 to negative 80, again we can just start with negative 80 minus negative 48, negative 32. So it is quadratic because the second differences are consistent. Again, we can look at negative 112 minus negative 80. So negative 32 again. And I think you'll find if you do the last one, you also get negative 32. So that was enough information for us to determine that this is definitely quadratic. All right, let's look at the next one. It says Joey's fixture began leaking water, so he called a plumber to help him fix the problem. The plumber said he would charge $100 for making a house call and $60 for every hour he is working there on the problem. What type of function, linear, quadratic, or exponential, would best describe the amount the plumber charges the customer? Can you write the function in this case? Well, in this case, let's just first look at the differences. So they're very nice to us, and the x's are 1 hour, 2 hours ago, so it's another 1 between those two. It's 1 between those two, so it's nice. The x's all jump by 1, and then here it jumps by 60. 100 to 160 is 60, and then from 160 to 220 is up by 60. So this one's really straightforward. It's linear because the first differences are the same. What I say by first differences is the difference between those two. So it's definitely linear. And we could write a cost function. So let's say cost of, or how much they charge of t. They said that he starts with an initial value of 100, and then he adds a rate of 60 for every hour, so that'd be 60 times t. So 60 times every hour, so that's how we would write the function for that one. Got the next one. It says a pot of tea is brewed such that its temperature was 200 degrees Fahrenheit, and then the stove was turned off. The pot of tea slowly cooled back to room temperature to 80 degrees over the next few hours. The data shown below is in the table. What type of function, linear, quadratic, or exponential, would best describe the temperature? All right, again, let's look at the first differences to see if that helps us determine what it is. So the x's are nice. They're going up by 1. All right, from 200 to 140, you could use a calculator if you need to, but that's down by 60, so that'd be negative 60. From 140 to 110, that's down by 30. From 110 to 95, that's down by 15. And from 95 to 87.5, that's down by negative 7.5. So I definitely see a multiple here. It's multiplying by 1/2 each. The differences are half of 60 is 30, half of 30 is 15, half of 15 is 7.5. So that tells me for sure that this is an exponential model. Anytime that the first differences are a multiple each time, it's exponential. Okay, which of the following would best be modeled by linear quadratic exponential function. A company named Phone Phase Foundry designs the hardware for new smartphones and is offering a new employee initial salary of $40,000 a year and will get a raise of an additional $6,000 for each year she works for the company. What type of function linear, quadratic, or exponential, would best describe the employee's salary based on the number of years she works for the company? Can you determine this function? Sure, we can call this, let's call this salary of t, so I'll call it S of t. And we start off with the initial base amount, which is 40,000. And then to that, we're going to add a rate, which they gave us every year she works, she gets an extra 6,000. Where t is in years. T equals years worked. And S of t is the salary, so that's pretty straightforward, I think, in this case. We started with a base of 4,000, we added 6,000 for every year worked. A company named Phone Program Ring designs software for new smartphones and offering a new employee initial salary of 40,000 again a year, and will get a raise of an increase of 12% each year he works for the company. What type of function, linear, quadratic, or exponential, would best describe the employee's salary based on the number of years that he's worked for the company? Can you determine this function? Again, I think we can do that as well. Let's call this one S of t again, but use a different color maybe. So S of t, again, t will be the number of years worked. Sure, I want to write lowercase or uppercase. I'll go back and fix that in a second. So again, we start with a base of 4,000 or 40,000, but this time we're going to multiply it by a growth factor because this is an exponential function like we've done in the past. So it's growing, so let's figure out what the growth factor is. When you do exponential problems like this is exponential anytime it's growing by 12%, we would take 100% and we'd add the 12% because you get 112% each year, so the growth factor is 112%. Which that's written as 1.12 because anytime you want to write a percentage as a decimal, you just move it back 2 places or divide by 100, and that's raised to the t for every year worked. So it's the base times the growth factor raised to the t. It says which company would provide a better salary after 2 years of employment. Well, we can figure that out for each of these. I think I want to change the name of this one so it's something different. Let's call this one money. Let's call this M of t, so I have different labels for my functions. Alright, so first we're going to figure out for 2 years. So 2 years at the first job would be S of 2. So that would be equal to 40,000 plus 6,000 times 2. I really probably should have used a different color for that. And if you plug that into the calculator or evaluate that, that's 40,000 plus 12,000. That would be 52,000 after 2 years. So after 2 years, the person would be making 52,000. And then let's compare that with M of t. So we'll do M of 2, and that's going to be equal to 40,000 times 1.12 raised up to the 2. And I think I'll use my calculator to help me with that one. So 40,000 times 1.12 raised up to the 2 for the growth factor. All right, so in this case 50,176. So it looks like you make more money with the first one for that one, but remember exponential eventually outgrows the linear or quadratic, so let's look at it in 8 years and see the difference then. So again, we'll do S of 2 is equal to 4, or not S of 2, sorry, S of 8, because we're doing 8 years this time. So again, we'll start with 40,000 plus 6,000 times 8. I think that's going to be, looks like if you do 6 times 8, that'd be 48. So 48 plus 4, it should be 88,000. So a fairly nice salary. So 40,000, let's just type it in, plus 6,000 times 8. So you can see it comes out to 88,000. And then compare it with the second salary, M of 8 is equal to 40,000 times 1.12 raised up to the 8. And let's see how much that would earn. So 40,000 times 1.12, the growth factor raised up to the 8. $99,038.53. So that would be substantially more if you worked for the company for a couple years and used the exponential model. So that would be $99,038.53. So if it's a long time you're working for the company, you're better off with exponential. If you're going to only work with the company a short amount of time, it'd probably be better to just use the linear in this case. All right, I hope this was helpful. I'm going to stop here and I'll start the next video in just a moment.